Yesterday we addressed the question of the multiplicity of solutions thrown up by the mathematical solution of the differential equation, and we have found that if certain additional information which is outside the scope of the differential equation is also incorporated into the knowledge that we have of the various solutions, then it becomes possible to select out of all the possible mathematically acceptable solutions the one which corresponds to the actual physical system. Thus, we are able to get, using the mathematics of solving a differential equation and using the additional information available, a unique solution to the equation, to the behavior of the system, which will match the actual behavior of the physical system. Having followed up this matter to this extent, we can now go on to studying certain other relationships between the mathematical model of physical systems and the systems themselves. So, one of those important issues that we will now address is what is already known to us, is called linearity. Earlier in this course, we have made a definition of what we have called linearity. We said that if we have a system that has an input and an output, and if the input is say x of t and the output is y of t, then we will say that given that the system transforms x t to y t, this same system, if it is linear, can also be depended upon to map certain other signals related to x t to other signals related to y t. In short, instead of x t, suppose I applied k times x t, then the property of linearity would ensure that the output corresponding to this new input would simply be k times y t. This is the property that we call homogeneity. There was another aspect to linearity which we called additivity. This was concerned with applying two entirely different signals or the sum of two entirely different signals simultaneously to the input. In short, here suppose you have x1 t, which when applied alone to the system yields a response of y1 t. If you had x2 t, which when applied alone to the system yielded an output of y2 of t, then the combination of the two inputs, by which of course we mean the sum of the two inputs, not any other kind of combination, namely x1 t plus x2 t, would elicit a response equal to y1 t plus y2 of t. This is what we know is the case with any linear system. So, a linear system should follow both the homogeneity property, namely this, as well as the additivity property, which is this. If it follows both these, then we will say that the system is linear, and we can summarize both these properties into a single defining equation by saying that given these two inputs x1 and x2, which correspondingly yield outputs y1 and y2, then if we applied say k times x1 of t plus L times x2 of t as the input, then the property of linearity would ensure that the output corresponding to this combination would be k times y1 of t plus L times y2 of t. This was just a recoup of what we already know. Now, let us see how a system described by a differential equation, which we have already solved, will behave, and see how that behavior relates to this definition of linearity. Let us take the same old circuit we had, which involved a resistor, a capacitor and a battery with a switch which was closed at t equal to 0. If we go to that, we will recall the equation we got for the solution. The solution in that context was the equation for the capacitor voltage as a function of time, the expression for the capacitor voltage as a function of time. We had V c of t given by V 0 minus V e to the minus t by R c plus V, where V 0 was the voltage of the capacitor at the reference instant, that is at, in this case, t equal to 0. By the reference instant, I simply mean the instant at which the auxiliary conditions have been supplied. So, with this we have over here. Now, let us see what is the input over here. Input is the DC signal V. The output is V c of t. So, let us relate it to the block diagram we had over here by making another block diagram. What we called x t is now equal to V, and what we called y t is now equal to V c of t. In addition, we know that some more information needs to be supplied, and that information we have called the auxiliary condition. That too needs to be fed into the system to get the unique solution y t, and let us plug that in somewhere from the top by saying that the initial condition, namely the auxiliary condition for the time instant used as the reference, is V 0 equal to V c of 0. This is the auxiliary condition. Now, this diagram captures everything there is to be captured. Now, let us see, is this system or is this equation capable of being linear with respect to x t, namely the input voltage V, the battery voltage V. It is easy to check. We will use the general definition of linearity by taking a linear combination of two battery voltages V and V dash. Let us scale the first one by say alpha and the second one by alpha dash. So, let the new input be alpha V plus alpha dash V dash. That is the input. The auxiliary condition remains V 0 equals V c of 0, and the output, we will see what the output is. Going by the equation we have, which was that V c of t equals V 0 minus V times e to the minus t by R c plus V, which is equal to V 0 e to the minus t by R c plus V times 1 minus e to the minus t by RC. This is the expression for the output when V was the input. Now what about the response for the new input? The new input is if we substitute this quantity in place of V in the expression for Vc, what do we get? Let us see. We get Vc of t, namely y of t, equals V0 e to the minus t by RC, which has no room for the input V. This term is independent of V, and then we have alpha V plus alpha dash V dash times 1 minus e to the minus t by RC. This is what we have. If the system had really been linear, according to our definition of linearity, which we had a couple of slides ago, namely this definition of linearity, then we ought to have got alpha V0 minus V e to the minus t by RC plus V plus alpha dash V0 minus V dash e to the minus t by RC plus V dash. If the system had been linear, we ought to have got this. What is the difference between these two expressions? The expression above and this second line that we have written. Simply that on the one hand we just have a term like V0 e to the minus t by RC in the actual physical system, whereas this stands in contrast to alpha V0 plus alpha dash V0 e to the minus t by RC in the assumed linearity of the system. There is clearly a problem because these two things do not match. Are we to say that this system described by this equation, by the differential equation which we solved and have found an expression for the output yt equals Vc of t, are we to say that this system is not linear? Clearly the answer is yes. So it is not linear. What can we do about this? Let us take a close look at the discrepancy between these two equations. You will see that in the discrepancy, which is indicated by this particular line, where on the one hand you have this in the actual system, and on the other hand you have this in the theoretical expression for linearity. In both these expressions you find that a common factor that figures in both expressions is the auxiliary condition V0. This is the cause of the discrepancy. If V0 had not been there, which is equivalent to saying that if V0 were equal to 0, then let us see what happens. The expression for the combined input x t equal to alpha v plus alpha dash v dash becomes v c of t equal to the term now on the right side corresponding to V0 will be 0 because V0 itself is 0. So, V0 e to the minus t by R c will be 0, and so you just get alpha v plus alpha dash v dash times 1 minus e to the minus t by R c. This is what you get. Let us just expand this a little. This equals alpha v times 1 minus e to the minus t by R c plus alpha dash v dash times 1 minus e to the minus t by R c, which is exactly of the form alpha y1 of t plus alpha dash y2 of t, where y1 was the response to v and y2 was the response to v dash. So, the system is now perfectly linear. That is nice to hear, but this was possible only when we made a certain sacrifice or introduced a certain constraint. The constraint was that we had to keep the auxiliary condition at the reference instant equal to 0. That is to say that this can happen only when the auxiliary condition specified at the reference instant is set to 0. Otherwise, the system is not linear. All right. Now, let us just explore this from a different angle. Suppose we say that in some sense Since the output, the ultimate unique output yt is determined or affected both by the input signal V or xt as well as the auxiliary conditions. Suppose we try to explore the relationship between possible changes we apply in the auxiliary condition and the corresponding outputs that result. Going back once again to this pet equation of ours, Vc of t equals V0 minus V e to the minus t by Rc plus V. We shall now see what happens when we replace V0 by some alpha times V0. We are not changing the choice of reference instant. All we are doing is changing the value of this auxiliary condition at the reference instant. Suppose we make this change, then we have to go back to this equation and replace V0 by alpha times V0. Then the output Vc of t will evaluate to V0 alpha times V0 e to the minus t by Rc plus V times 1 minus e to the minus t by Rc. Now we find that there is a certain change in the output, but there is a change only in that part of the output, in that term of the output that contains the auxiliary condition as a factor. There is no change in the other term in the output where the auxiliary condition is not involved. So, on the whole, suppose we again ask the same question, is this system linear or not? Is this linear with respect to V0? The answer is no. Not linear. Taking a cue from what we did last time, let us see if there are any constraints we can impose upon this system in order to make it, to force it to be linear with respect to the auxiliary condition. Again, the answer just stares right at us in the face. You can see that there is a separate term over here that involves the input, namely V, and it is this term which is refusing to scale, because after all, if the entire system had been linear with respect to the auxiliary condition, then what would we have got? That is, if the system were linear, we should have got Vc of t equals alpha times V0 minus V e to the minus t by Rc plus V. All right. that would expand to alpha v 0 e to the minus t by r c plus alpha v 1 minus e to the minus t by r c. This is what we should have got if it had been linear with respect to this auxiliary condition, but that is not what is happening. What we are seeing is that there is this term which is different in the two cases. In the case when we are assuming linearity with respect to the auxiliary condition, and in the case where the actual equation is being evaluated by replacing V 0 with alpha V 0. This is the cause of the discrepancy. So, given that the term containing the cause of the discrepancy is the term that contains x t equal to v as a factor we could force the system to behave linearly with respect to the auxiliary condition by just setting x t equal to 0. By setting the input v equal to 0, we would get perfect linearity, because then V c of t would simply be equal to alpha times V 0 e to the minus t by r c. It would be linear. Hence, the summary is as follows. Linearity with respect to the auxiliary conditions may be enforced by keeping the input at 0. So, to summarize all that we have observed so far, let us put down both these lessons that we have learned. A. Response is linear to input if the auxiliary condition is 0. Linear against input is 0 at the reference instant, lesson B. Response is linear with respect to the auxiliary condition when the input x t is set to 0. Clearly, the problem of the whole system not being linear either with respect to the input or with respect to the auxiliary condition is happening because we are adding two different things. In short, we can almost say that the output or the response consists of two components. One component that is referentially linear with respect to the input, and the other component which is similarly linear with respect to the auxiliary condition. But when you add the two together, the combination is linear neither with respect to the auxiliary condition nor with respect to the input. So, this makes it very attractive for us to actually write out the solution y t or the response y t as a sum of two separate components. Let us do that. Let us write that y t equals y a t plus y I t. Y a t is the response y a t is the response when input is 0. And y I t is the response when the auxiliary condition is 0. So, this has brought us to a certain position of understanding, to a certain level of understanding. We only need to put all these things together and also do a little generalization. What happens when you have more than one auxiliary input? This is what we need to look at next. So, what do we think will happen to a system which is of higher order and therefore requires multiple auxiliary conditions? Without trying to prove these things, let me just tell you that the most natural thing will happen. Since the circuits or the systems which are of our concern are linear, each auxiliary condition will just have to be treated separately and the system will turn out to be linear to each auxiliary condition individually, but of course not to the combination of them. In order to explain what this means and to put it down in terms of clear equations, let us just make a few notational announcements. Let the equation being solved be of order n, then there should be n auxiliary conditions. There should be n auxiliary conditions. So, all we can let us call these auxiliary conditions y 0, y 0 1, y 0 2 and y 0 n. These are the n auxiliary conditions. Further, let us say that we can force all the auxiliary conditions except one to be 0 as well as the input to be 0 when we choose to do so, and observe the response of the system to just one particular auxiliary condition not being 0. In short, let x t be equal to 0, also let y 0 k be equal to 0 for k equal to 1, 2, n except for k equal to small n, which is some number 1 lying between 1 and capital N. So, that particular auxiliary condition is not 0, that is to say that y 0 n is not equal to 0. All other auxiliary conditions are 0. Then it will turn out that the response, please note that x t is also 0, the input is also 0. Then the response I will denote by y t equal to y a n of t. That is to say, that is the response when only the nth auxiliary condition is non-zero and everything else is 0. When this is the case, what happens if we scale y 0 n by some factor alpha n? Is replaced by alpha n y 0 n, then the response becomes this, the response becomes this. However, okay, and when we say that the response is this, that seems to indicate that the system is linear, it is homogeneous with respect to the choice of alpha n. So, it is linear when all other auxiliary conditions as well as the input are 0, it is linear with respect to the particular auxiliary condition which is not 0. Fine. Now, suppose all the auxiliary conditions were non-zero, but only the input was 0. That means to say we are just considering a simple situation where only the input is 0 and you have a set of non-trivial auxiliary conditions y01 to y0n. Then the output would be decomposable as y of t equals summation y a n of t, n running from 1 to n. Hence, the relationship for linearity would simply be to say that if we scaled each of these individually by alpha n, then the total output y would be the sum of the respective scaled responses. So, you would get a scaling. If we scale y01 by a1, y02 by a2, let us make it alpha 1 and alpha 2 just to maintain our habits. If we scale y01 by alpha 1, y02 by alpha 2 and y0n by alpha n, then what we would get as the output would be y of t equals summation n equals 1 to n alpha n y a n of t. This is the response we would get. All right. Now, let us keep this in mind and also apply a compound input consisting of several component inputs x1 t, x2 t, xm t. xt is replaced by a compound input beta m x m of t and the system response to each individual unscaled component input x m of t was y I m of t, then the overall response when all auxiliary conditions were set to 0 and input summation m equals 1 to m beta m x m of t is applied, would be y of t equal to summation beta m y I m of t for m running from 1 to capital M. So, this would be the complete response to all the inputs, where each respective input x m was scaled by beta m. You would just get the sum of the scaled corresponding outputs. All right. Now, suppose we put everything together into a single equation and say that we also have a set of auxiliary conditions running from y 0 1 to y 0 n, which we scale by alpha n or alpha 0 alpha 1 to alpha capital N, and a set of inputs x m running from 1 to n, which are all scaled by beta m respectively, then let us see what would happen. We can now write the complete grand equation relating to that describes the linearity behavior of the system. Auxiliary conditions, alpha 1 y 0 1 on to alpha capital N y 0 capital N. This is the complete description of the data that should go into the solution, all the auxiliary conditions and all the component inputs. Then we would get y t in the form of the sum of two parts, m equals 1 to m beta m y I m of t plus summation small n equals 1 to capital N, the set of responses due to the individual auxiliary conditions, alpha n y a n of t. This is what we would get, and this essentially summarizes the entire linearity behavior of the linear constant coefficient differential equation that represents the physical system. We can see many things in this, but the most simple way of describing this whole thing is just that this consists of capital M plus capital N different components, and while the entire response is linear with respect to each component of this m plus n different components, it is that linearity is visible only when that is the only component which is non-zero and all other components are 0. When more than one component is non-zero, then linearity has to be defined in this manner that we have put down over here. This completely describes the linearity behavior of the system. All right. One upshot of what we have learned today is that it is instructive and attractive to consider the output of a system described by a differential equation to consist of two component parts, the component part arising out of the auxiliary condition and the other component part that arises out of the actual input being applied. So, this is a certain kind of decomposition. Now, there is a different terminology for what we have done, and I will just now mention this terminology to you. Y I of t, which I called the response due to the input with the auxiliary conditions being set to 0, is called the 0 state Now, what does this really mean? It simply means that the system, the condition of the system as described by the auxiliary conditions is what we are calling the state, and we are saying that if all the auxiliary conditions are 0, then the response of the system due to the input x of t would be the 0 state input, the 0 state response, sorry, this is the 0 state output or the 0 state response. That is to say, it is the response due to the pure input. When the state is 0 and the response is only due to the input. Y A of t is termed the 0 input response, because it is the response you observe when the input is 0, when x t is kept at 0. This can alternatively and instructively be termed as the pure state response. Now, we can simply say that the overall system behavior is linear in two different senses. It is linear with respect to the input when the state is 0, that is to say that y I of t scales with the input, and the second statement of linearity is that the system is linear with respect to the state, where we can now describe the state by a single vector y01 to y0n. Now, it is to say that it is linear with respect to the state is to say that all the arbitrary all the auxiliary conditions are scaled by the same component, say alpha, by the same factor, say alpha. If we do this, then the overall response y of t would just be, in the absence of course of any input, would just be equal to y A of t also scaled by alpha. In short, if you put this down, we will say if the state is given by y01, y0n, then we will say the scaled state is alpha times y01 to y0n, which is equal to alpha y01 to alpha y0n. Fine. If we say this, then we find that the response when x t equals 0, which is to say the pure state response, would be y t equal to alpha times y A of t, where y A of t is the pure state response when the state is y01 to y0n. And the input is 0.